The title of my talk is Near-Earth Radiation and the Plasma Environment Community Approach to Model Validation. The topics, the elements to be covered in this presentation include the following. To assess the performance of space environment models, so the near-Earth radiation and plasma environment community that is within the International Space Weather Action Teams address this issue from a systematic, user-oriented perspective by leveraging previous community efforts. And also, I will cover the information regarding how we define the essential space environment quantities that are to be used for model validation, and how we determine such quantities, and the metrics, various metrics used for such effort, and measure of the uncertainties, and also the archive. So none of these are trivial. So near-Earth region is really a critical region for space weather due to its diverse particle and plasma population. It can have a slew of impacts that include surface charging, internal charging, single event effects, and total dose, and also radiation impacts on aviation. So the details of these can be found in our 2019 publication on space weather. So what's required of these essential space environment quantities are, they should be directly measurable, and better yet, they should be available over a long period of time, and also should be easily translatable to space weather impacts, and so can be understood by the end users, by the spacecraft operators, and should be applicable to most use cases. That means, should be relatively universal. And for use cases, there are different situations, such as the case just for situational awareness, or forecasting during the mission operation phase, or during mission planning, or scheduling some specialized campaign. Then there's a timely anomaly resolution. So the operators need to quickly identify whether anomaly due to environment or whether due to the electronics. And then there's a in-depth post-event analysis that will usually value model with a higher accuracy than timeliness. Hey, all these cases exist, and these essential space environment quantities should be applicable. And by leveraging the effort from previous community events, like over the last few years, we have chosen and defined the essential space environment quantities for all these 5 impacts. And these quantities, they really utilizing the community expertise from scientists, from users, and from the past anomaly database. So they are drawn, they are chosen because these quantities are more related to the anomaly types mentioned here, and also they are measurable. So the second column are these quantities, essential space environment quantities, and the time period that matters to this effects, and also effect quantities that we can translate to effects very easily understood by the end users. And such model validation work already has a good start. There's these few papers mentioned here document the progress. And when we do such validation, there are choices of different metrics. There are traditional ones and novel ones. So the traditional ones, there are a few mentioned here, and novel ones that utilize the log accuracy ratio, so more relevant for flux and fluence, that type of quantities, and also the statistical sense ones. And besides this, we also have categorical skill scores, like event detection type. They are usually threshold based. Say there's the often mentioned one, Heidegger skill score, and the recent mention or proposal of using stone or records for such event detection metrics. So these different metrics will reveal different aspects of model performance and capabilities. So whenever applicable, we should try to use different, more metrics, more types of metrics to review these different aspects of the model. NASA has a standard initially for engineering use, but it can be really relevant for our model validation efforts. So these are the 8 factors in credibility, model credibility assessment. These are mentioned here. The data pedigree means quality of the data, verification, and validation. That's we know verification is verifying the underlying physics, validation to compare how the model results compare with the observations. And there is an input category. When you use the model, there is input data, input condition, and the uncertainty characterization, and whether the model is robust or not. So it's very important for models involved in operations. And also the supporting evidence. It's like the version control, the process management. So it's when we do the model validation and especially track the performance over a long period of time, all these should be really documented and tracked. And here giving you example in our model validation effort in surface charging. So in contrast to the traditional ones, we choose the event and that has actually the surface charging anomalies occur during such period. And then we use the ESEQ, the greater than 10 keV electron flux as the quantity for validation. And here is we did 5 model runs and compare with the Valen and probe A and B observations. And details can be found in this paper. And what I like to mention is that it's really depends, the model or the specific run result depends on the metrics used. So here's the table document the result, and top shows the different metrics across correlation, prediction efficiency, yield, the mean square error, and the SSPB is the symmetric sign percentage bias using log ratio. So we can see not any single run perform the best across the board. So it depends on the metrics. Some has a better performance for a specific metrics, and as they review different aspects of a model. So our next steps is to define the clear guidelines for carrying out more model validation for different impact types, and also assess the model performance using a set of grid-upon metrics at different levels, complexity and also comprehensiveness, and do so for different use cases. And we will keep a detailed archive or database of the key model ingredients, like the 8 elements or factors mentioned before, and also include the model history and so on. And the CCMC has already started the method data registry, which include kind of like a tracking of models, model version, and model details, and also observations. There are details and different level of qualities and so on. So it's really a step towards this direction. And also CCMC, we're also building the Camel 2, Lutz Rastetter going to talk about that, and to actually facilitate such model validation, and it has built-in metrics for different types of model validation. So this is once again a reminder of all these elements. So we should keep that in mind when we do our model validation, especially when we do the archiving. So the final remarks and outlook for such model validation approach. They will help transitioning models to operations, and also help us identify model deficiency and knowledge gaps, and help identify measurement needs, and also help building application tools. So this model validation approach also involves continue working with the users and to understand their needs. And we hope to continue this under the ISWAT initiative, all these falling under the G3 cluster, the near-Earth radiation and plasma environment. And we invite you to participate, not only for those who are involved in the models, and also those who are involved in observations. So we really need all these elements come together to do this more efficiently. Thanks.